All right, this lesson is on PVTn problems and solving for pressure, temperature, volume, and number of particles, specifically for problems that involve temperature. So our objective for this lesson is, again, to be able to predict changes in pressure. The way that we're going to do this is by using proportional reasoning. Now remember, proportional reasoning is just a fancy way of saying we're going to be using fractions to do these calculations. So a really important skill is going to be recognizing fractions that are larger versus fractions that are smaller. So I'll give you an example of this below. If we were comparing 3/2 versus 2/3, which fraction is larger? Well, 2/3 represents a pie that's cut into 3 slices, but we only get to eat 2 out of those 3 slices. Whereas 3/2 represents a pie that's been cut into 2 slices. And we get to eat 1, 2, and 3 slices. But where does that third slice come from? Well, it actually comes from a whole nother pie that's also been cut into 2 slices. So in which case do we get to eat more pie? Well, the case on the left is the bigger fraction. This fraction is a bigger fraction because it's what we call an improper fraction, which means that the numerator is a larger number than the denominator. So whenever we're comparing fractions, keep in mind that improper fractions are always going to be larger fractions, whereas a fraction on the right, a proper fraction, where the numerator is smaller than the denominator, is going to indicate a smaller kind of fraction. So let's use these proportional reasoning skills to predict some changes. So you're planning a road trip to Colorado. The pressure in your tires in Arizona at 52 degrees Celsius is 103.4 kPa. What will the pressure of your tires be in Colorado, where the temperature is 31 degrees? Volume and number of particles equals constant. So what I'm going to do is I'm going to color code all of the information that's relevant to solving the problem in this question. Specifically, I'm going to color code all of the numerical information. So 52 degrees Celsius, 103.4 kPa, and 31 degrees Celsius. All of this information is going to go into my table. I just need to make sure that it goes in the correct location, as well as make sure that it's in the correct units. So if I go through my table, my first column is pressure. In the problem, it tells me that the tire pressure starts at 103.4 kPa. So my initial pressure is 103.4 kPa. The other information that they tell me is about temperature. Now keep in mind, and I'm going to make a note up here at the top, when we were talking about graphing pressure versus temperature, when we graphed our temperature in degrees Celsius, we saw that our line did not intersect at 0, 0. In other words, when temperature is 0 degrees Celsius, pressure is not 0. However, when we graphed pressure and temperature in Kelvin, we saw quite the opposite. We saw a line that went through 0, 0. Because when temperature is 0 in Kelvin, pressure is also 0 in Kelvin, since particles are not moving. So when we do calculations, we want to use temperature in Kelvin because our relationship is directly proportional. In other words, pressure and temperature do the exact same thing. They increase together, they decrease together proportionally. So when I'm looking at my temperatures, 52 degrees Celsius and 31 degrees Celsius, I need to convert those into Kelvin before I can put them in my table. So keep in mind that we can convert temperatures into Kelvin by taking our temperature in degrees Celsius and adding a specific value. That specific value is 273.15. Oops, that should have been an addition sign. Whatever we get from adding our temperature in Celsius to 273.15, that's going to be our temperature in Kelvin. So if I wanted to convert 52 degrees Celsius into Kelvin, I would need to take 52 and add 273.15. Let's get rid of that add. And I would get a temperature of 325.15. Oops, let's get that out of here. And I might need to make my pen smaller, but we'll try. So my initial temperature in Kelvin is 325.15. To convert 31 degrees Celsius into Kelvin, I need to do the same thing. So 31 plus 273.15 gets me a temperature of 304.15. Now they told me that volume and number of particles stay constant. So that means these two columns are not going to be used. So if I look at my temperature is getting smaller, meaning it's decreasing. I have to predict how is this going to affect my pressure. So I really need to think about what's going to happen to the collisions in a box full of gas. If these particles go from moving quickly at a hot temperature to slowly at a cooler temperature, are my collisions going to increase or are my collisions going to decrease? Are the particles going to collide more often with the container or less often? Well, if they're moving slower, that means that there are going to be less collisions occurring less frequently with the box. So if there are fewer collisions, that means my pressure should decrease. So now that's going to help inform me of what it is that I need to do with my pressure. So if my pressure needs to decrease, what that means is I need to multiply my pressure by a fraction that's going to make my pressure become smaller. In other words, I need to take my pressure and multiply it by a smaller fraction. So my pressure of 103.4 is going to be multiplied by a fraction. The numbers that go in that fraction are going to come from my temperature. So I have to decide, should 304 go in the numerator or the denominator? Well, if I need a smaller fraction, my smaller number should be on top. And the larger number, 325, should be on bottom. So let's go ahead and multiply this and see what we get. So 103.4 times 304.15 divided by 325.15 gets me 96.7 if I'm rounding to the tenths place. So my pressure is going to be 96.7 kPa. So when I drive from Arizona to Colorado, the change in temperature alone is going to decrease my pressure to 96.7 kilopascals. So let's do another example like this together. Okay, so let's say Ashley likes to keep lotion in her car. If her Bath & Body Works lotion is normally stored at a temperature of 25 degrees Celsius, how will the volume change when it's stored in a warm car at 40 degrees Celsius? So they gave me two numbers. It looks like they're missing a value. So normally they would give you a value for the volume of the lotion. In this instance, it appears like they might be wanting you to solve the problem without that value. On the test in the very near future, that will not be the case. So I'm going to give you the volume of the lotion initially to be the standard 250 milliliters. So we're going to use that as our initial volume. Could we solve the problem without this value? Yes. But But again, that's not going to be something you see in the very near future, so we're going to focus on what you will see in the future. So I have my initial volume. They didn't mention anything about the number of particles in the lotion changing, and they didn't mention anything about the pressure of the lotion changing. They just talked about the temperature and the volume. So I need to take these temperatures and convert them into Kelvin to put them in my table. So 25 degrees Celsius plus 273.15 is going to get me a temperature of 298.15 Kelvin. I'm going to do the same thing with my 40 degrees Celsius, and that's going to get me 313.15. So now that I have all the information, I can see that my temperature increased in this case and went from a small number, 298, to a larger number, 313. So the question is how is this going to affect my volume? So if I have a box with particles that are moving slowly, and then those same particles start moving fast, how is that going to affect the volume of the box? Well, if we think back to our thermometer with the red liquid inside, when it gets hot, what does it do? It expands. So it goes then that if these particles start moving more quickly, the volume is going to expand as well. So my volume should increase in this case. Now, if my volume's supposed to increase, that means I need to take my volume and multiply it, not by a fraction that's going to make it smaller, but a fraction that's going to make it bigger. So I need to take that 250 and multiply by a bigger fraction so that my volume will increase. So that's exactly what I'm going to do. So I'm going to take 250, multiply it by a fraction, and since the volume has to increase, that tells me that 313 should be in the numerator, and the 298 should be in the denominator. This is a bigger fraction because it's improper, since the numerator is larger than the denominator. So let's go ahead and plug this in the calculator. 250 times 290, oops, I typed that wrong. That's clear. 250 times, 313.15 divided by 298.15 gets me 262.6. And the units on this are going to be the same as my units before, which will be milliliters. So the volume of the lotion would expand to 262.6 milliliters. So this last one is a try. Go ahead and attempt it. Pause the video and check your answer when you're done by unpausing the video. Okay, I'm going to assume that if you're listening to this, that means you've already attempted the problem and you're ready to check your answer. So a party planner is decorating for a client's birthday party with balloons at 25 degrees Celsius. Without thinking, she leaves the balloons outside in the summer sun at a temperature of 37 degrees Celsius. If the balloons were initially 670 milliliters in size, what will their new volume be? Pressure, number of particles is constant. So first thing, I'm going to cross out pressure, number of particles. So those are constant, so I don't need those columns. Initially, the volume was 670, and my temperatures are in Celsius, so I need to convert those into Kelvin. So 25 plus 273.15 gets me an initial temperature of 298.15. 37 plus 273.15 gets me a temperature of 310.15. Sound like the last problem? Very similar, but not exactly the same. All right, so my temperature increased. So the question is how is that going to affect my volume? Well, if my particles are moving slowly, they're going to be condensed. And if they start moving faster, they're going to spread out and expand, which should increase the volume of these balloons, which means that I need to take my volume and I need to multiply by a big fraction. So let's go ahead and take this 670 and multiply it by a bigger fraction. So should 310 go on top or on bottom? Well, big fraction means the bigger number should be in the numerator, and the smaller number should be in the denominator. So I'm going to go ahead and multiply this in the calculator. 670 times 310.15 divided by 298.15 gets me 696.96, which is really going to round up to 697. And my units are going to be milliliters, same as they were for my initial volume. So that concludes this lesson. Go ahead and move on to the independent practice.